feel free to stop and ask me questions. I mean, you can shout out or raise your hand if I'm not looking. Just shout something out if you have a question. So don't feel bad interrupting. It's supposed to be a workshop. So but the way I formatted it is it's basically it's introduction to computational finite element analysis. I highlight that because you can do hand finite element analysis. And while I'll talk a little bit about that, this is kind of going into how you're going to use software to perform FEA. So the presentation is going to cover just FEA intro, setting up a FEM, which is a finite element model, interpreting the results of the model, some general tips, how to present your results, and then I'll do some example cases. It's not meant to cover detailed, FEA theory through hand calcs, and I'll introduce that a little bit, but that's not what I'm trying to focus on. Or a step-by-step SolidWorks tutorial. In fact, this was meant to be a general FEA, so you could use any software. So this is kind of trying to lay the foundation where once you understand how computers do FEA, you could use any software and have it run a successful FEA. That was my intent of this. Since you guys are using SolidWorks, I want to do some examples. I do run into some simulation, and a little of this is specific to SolidWorks simulation. And I use a different FEA. So I actually just learned a couple weeks ago. So I'm not like super expert on the SolidWorks simulation, like exactly how to do everything, but I know how to run FEA on other software, right? So this was kind of, it's like some of this stuff you probably can't, that I'm going to talk about, you may not even be able to do in SolidWorks simulation because, it may not be as powerful as some other ones. So I just wanted to be upfront with that's kind of my intent, was I want you guys to have the knowledge, a good foundation, and then it doesn't matter what software you're using. And then it's based on static analysis. So I'm not talking about how to do dynamics, because you will need to know more things if you want to do dynamics, especially thermal. Nonlinear is a whole nother topic, right? And I'll talk about what nonlinear means as far as FEA. Modal analysis, transient analysis, shocks, buckling, fatigue, or composites. Now, composites is not that much different than what I'm going to show you for static structural. It's more how you build an element, but I kind of put all these down so you understood that there's a lot of different types of analysis, and you'll set up your model differently if you're doing a different model than static structural. Okay, so this says, what is FEA? FEA is finite element analysis. The other acronym we're going to be using is FEM, which is a finite element model. Similar to say, if someone says, hey, do you have a CAD of that A-arm? You expect a 3D geometry file, right? If I say, do you have a FEM? It's an analysis file with the geometry and the mesh and all that stuff. The main objective of FEA is to break up large structures into smaller ones and then assess the larger structure by piecing it all back together, right? Another way to say that, right, you're trying to solve a large complicated equation by adding up the results of smaller simple, equations. And this smaller simple equation is the finite element part, right? There's a finite number, there's a discrete number of solutions you're adding up. And then the elements are small. They can be very small in some cases, but that's why it's called finite, and element is the breaking up parts. So the elements are these small structures, and they're connected together by nodes. This is kind of an example, right? You guys, so this is getting cut off. You guys probably already do finite element, and you don't even know it, right? Like if someone gave you this geometry, probably in 6th grade, you had to find the area of this thing. And there's no one formula you're going to say, find the area of this random shape, right? So what are you going to do to solve that, right? You're going to say, oh, I know the area of a square, and I know how to get the area of a triangle. So I'm just going to solve the area of this and solve the area of that, and I'm going to add them up, right? That's basically, the dumbest way I can kind of explain like finite element analysis, right? And so what you did was you made 2 elements, right? And you created those by boundaries, which are nodes, right? So that's kind of a real simple example of what finite element analysis is doing. This is further defining nodes and elements. So a node, is a point in space where there's degrees of freedom. And the results of FEA are going to be typically given at the nodes. So when you solve for deflections and stresses, it's nodal deflections and stresses. And I said typically because software will also give you elemental stresses. So when you do it, if it's an elemental stress, it's giving you the average of all the nodes that the element's touching, right? And that'll come in, that's kind of important in a later point I have about making sure you have enough elements through the thickness of material. So the nodes is really where all the math's happening, where you're kind of solving for all the outputs and stuff. The element defines how those degrees of freedom of each node relate to each other, right? And also how the deflections can create stress, right? So to get the stress from the node is you have to know how far it is from the other node, and what the element that's connecting the nodes has a certain stiffness, and that's how you're getting deflections and stresses at nodes. So here's a couple examples of element types. I'm going to go way deeper into this, so I don't need to talk too much about these. This is like the most common one is the tetrahedral. That's what when you do your solid meshes, that's what you're probably gonna see in SolidWorks simulation, is a bunch of tetrahedral meshes. But it can be as simple as a line between two nodes. That's an element. And then the difference between here is, and we'll talk about this soon, is that it's gonna linearly interpolate between the two nodes, right? And so there's actually other elements that you create the element and then it has these subnodes in between to get like a polynomial instead of a linear fit, basically, which is less common to see these. It's more computer time. So you typically see, this one, and then these simple 2D ones. Oh, actually, I did want to ask, figure out what kind of classes people have taken. How many? Raise your hand if you've taken statics already. Okay, so there's a couple who have. Raise your hand if you haven't taken statics. Oh, okay. Raise your hand if you have not taken strength of materials. Okay. So you guys are not allowed to run FBA, basically. So yeah, that's the minimum knowledge you need to be able to understand FEA and run it, right? You can watch YouTube videos of how to create a mesh and all this stuff in SolidWorks. You're not going to understand FEA unless somehow you have that knowledge and you just didn't take the class. But that's kind of the minimum requirements of that. So some of this stuff may not actually make sense. I'm going to talk about stiffness matrices and stuff like that. So I understand those are the two fundamental classes at minimum that you need to not just take, but have understood those to really be able to successfully perform FEA. So this is what the basic FEA calculations are. So you're gonna, it's just a simple deflection, stiffness times deflection is your force, right? So you have a force, it's all matrix algebra. So it's you have a force, and you can solve for any of this, right? So typically you know some of the forces, and then you know the displacements, right? Well, I'll get into that. So it's just force is the stiffness matrix, and then you're gonna get the deflection. So the displacements are calculated at each node, and then you have to know certain forces and displacements, right? You have to have certain knowns. So in this matrix, you're gonna set up where forces are, and then you're gonna put 0 for the nodes that don't have forces on them, and then for the displacements, you're gonna put 0 where on nodes you're constraining, right? And the rest you're gonna solve for. So you're gonna be solve for displacements, and once you have the stiffness matrix, right, you can solve for stress, right? And so that's basically what's going on. Keep in mind what K is. K is a couple things, right? It's the stiffness matrix, which is a cross-sectional area, it's lengths, and it's modulus, right? So that's what the stiffness matrix is. So any material, so material properties is going to change it, and your geometry is going to change your outputs. Okay, this is the basic form of the equation, right? This is the easiest form of this equation to think about. But for other kinds of analysis, it's very similar, but the parameters are a little bit different, right? For example, in thermal, that stiffness matrix is going to be thermal conductivity, and then that displacements is going to be temperatures at those nodes, right? So this kind of applies to most of it. That's what FEA is doing, is taking matrix and basically doing matrix algebra for you on a bunch of simple problems. Okay, so this is kind of the FEA process, and basically I'm going to talk about each of these things in the presentation. So you define the model geometry. That's the first thing, right? There's a part you want to analyze, right? So typically when you start drawing stuff, especially if you know you're going to do FEA on it, think about that ahead of time, right? So understand that you're going to do analysis and you want to make it simple to be able to do the analysis, right? So you want to keep it simple. If you can start and only do sketches, just do sketches, right? Now, for SolidWorks, you can use weldments, which I don't know if you guys are familiar with that, but you should be using weldments like to make frames. So all you do is have sketches, and then the weldments are in the toolbox, and you can define your own weldments, and then it just puts that geometry on the sketches for you, basically, right? In other softwares, you just use the sketches, and you just, in the finite element model, you just tell the tool what the geometry, cross-sectional geometry is. So you don't need any physical geometry besides sketches. And I'll get into that a little bit further, but that's the simplest way to do it, is just do sketches. Use like hole wizard instead of, if you have a part that you know has a hole in it, don't draw a sketch that has a square. You have the markers up here?
Yeah,
I don't know what's better to.
On the right.
If you don't draw a sketch like this and extrude it, okay? Draw this and extrude that, and then use the hole wizard and put a hole in it. Okay, that's more of a SolidWorks or a CAD tip, but it's gonna affect your FEA, because you're gonna see later you're gonna want to simplify your geometry and remove holes. And there's an easy way to do that when it's a feature. When it's embedded in the sketches, it's a lot harder. Also, if you want to make this a tapped hole later or whatever, it's just way easier if it's in your hole wizard to change that hole than to go into a sketch. And so you should always be using like features. Same with the fillets. I don't know if I think I wrote this somewhere. If you know you're gonna like have fillets here, don't draw a sketch that has fillets in the sketch. Okay, draw it a sharp square and use the fillet feature and make fillets. That way you can, same with the holes, you can remove it later and it's easier to change. And a lot of times you might like connect to a node in a sketch, that later gets changed or moved, right? So you should be doing that kind of stuff towards the end, like adding fillets and all that towards the end, so that you don't have parametric features attached to fillet surfaces and stuff like that. So think about this stuff when you first start drawing. It'll make it a lot easier to do FEA. No, and do not model threads. Never model threads. I mean, especially if you can do FEA. You should not have any threads in there. When you mesh it, it's going to try and mesh the threads, and it's not a good idea at all. So just do the pilot hole. That's going to be for the thread. I think there's an option in SolidWorks to show thread or not show thread. So okay, so you make your geometry. You define the analysis type, so you can then tell the software, hey, I want to do an analysis. It's going to know what type do you want, right? So the static structural, thermal, modal, dynamic, so you select that. And then you got to, pick the element type, which hopefully you kind of already thought about when you did this, right? Am I gonna use beams? Am I gonna use plates? And I'll get into all that stuff. So you have to decide what type of elements you're gonna use. Then you define the element geometry. Okay, if you're not using solid mesh, then you tell it the beam cross section, including orientation. Now in SolidWorks, I think if you're like using I don't think there's an option to do this. I don't think you can have a sketch and then just tell it what the cross section is. I think you have to have solid geometry, but that's like your weldment or whatever. But in other software, so if you're using other software, you literally just tell it this sketch has this area and this inertia. You don't even have to tell it it's an I-beam, it's a square, it's whatever. You just give it the A and the I. That's all it cares about. And then and it does matter where the shear center is and the neutral axis is, right? So you just put that stuff in, and then you have to tell it its orientation, right? So if you did have an I-beam, if you have a sketch, it doesn't know how to orient that I-beam. So you give it a vector and whatnot. So, I mean, it can be hard to keep track of, but that's part of the process, is define the geometry, whether you're doing it in the FEA or it's been done in the CAD for you. Then you define the material properties. You create the mesh, which is how it breaks up all the elements. And you want to simplify your geometry before meshing, removing holes and fillets. And then define your boundary conditions, which will make or break your model. Define the load cases, which also can make or break your model. Then you compute the results, you post-process it, and then you iterate this process until you come up with the design that you want.